Okay, so we're now up to section 3 of the syllabus. The clarity of the signal transferred can affect interpretation of the intended visual communication. In order for a visual signal to be interpreted, it must reach the photoreceptor cells at the back of the eye in a clear and precise form. It is transferred in the form of reflected, transmitted, or generated light from the environment outside the eye through the transparent layers of the eye to the retina at the back of the eye, where a focused image falls on the rods and cones. To achieve this, the eye has transparent structures that must be maintained to perform their function of refracting light to the correct degree so that the image may ultimately reach the retina in clear and in focus. So the 2 dot points for today's video are: identify the conditions under which refraction of light occurs, and identify that the cornea, aqueous humor, lens, and vitreous humor are refractive media. If you have ever tried to spear a fish in shallow water while standing on a beach or on a riverbank, you will know how difficult it is to pinpoint accurately the exact position of the fish. The fish that you see is actually an image, that is, reflected light that reaches your eye. In order to be seen, an object either reflects light, generates its own light, or transmits light to our eyes. The fish image that is seen is light that has been reflected through water, air, and then through your eyes. When light moves from one substance or medium such as water to another medium such as air, it is bent or refracted. This leads to a distortion of the image that you see, making it difficult to judge the exact location of the object at which you are looking. When light passes from one medium to another of a different density, the speed at which the light is traveling changes. As a result of the light speeding up or slowing down, the rays are bent or refracted. When you place a straw into a glass, it appears to bend. This distortion in the image is brought about by the manner in which the light reflects off the straw is being refracted. Light travels more slowly through the water at the bottom and quickly through the air at the top. Because movement of light in the denser medium is slower, it is refracted to a greater degree than the light traveling through the air. So this little video explains it a little bit nicer.
Light rays are bent or refracted when they pass from one semi-transparent medium to another. The refractive angle changes depending on the medium encountered. If a ray travels through air and enters a denser medium such as water, it is refracted towards the normal, a line perpendicular to the medium's surface. Rays entering a less dense medium will be bent away from the normal. If this occurs at a low enough angle, they are refracted 90 degrees from the normal. This is called the critical angle. If the ray's angle exceeds the critical angle, total reflection occurs. Light ray.
So, when light passes through a biconvex lens like this one here, the rays are refracted towards a central point known as the focal point, as we can see here. The rays then cross over and diverge or spread out from that point. If a screen is placed at a point in the pathway of the diverging rays, an image will land on the screen. The screen can be moved backwards and forwards until the image is clear and precise. The rays are said to then be in focus. If the image that falls on the screen appears blurred or is out of focus, this is because the focused image is falling either in front or behind the screen. It is interesting to note that the resulting image that forms once the rays are being crossed over is upside down or inverted, and we will be observing this in our investigation in class. The density of the cornea, aqueous humor, lens, and vitreous humor are all similar to each other and close to that of water. All of these structures refract light that passes through the eye to a greater or lesser degree. The refractive power of air, however, through which light travels to reach the eye, is quite different from and much lower than the refractive power of different parts of the eye. Therefore, the greatest degree of refraction in the human eye occurs when light moves from the surrounding air into the cornea of the eye at this point here, since the change in refractive power of the media is greatest at this point. So the refractive power of the air is 1, the refractive power of the cornea, is 1.38. So we have the greatest change occurring here. The lens is an interesting refractive structure in the eye. It is able to refract light to a great or lesser degree by altering its shape. This is termed accommodation and is useful in allowing the eye to adjust for near or far vision. The lens consists mainly of living protein fibers called crystallins housed in a lens capsule. These proteins are folded in a particular way to make them transparent. The overall shape of the lens, so its degree of curvature, depends on the degree to which the light can be refracted. And as we've already seen, it is these muscles and suspensory ligaments that help to change the shape of the lens, and that's what we'll be looking at in our next video. Also covering 2 dot points. Identify accommodation as the focusing on objects at different distances, describe its achievements through the change in curvature of the lens and explain its importance, as well as compare the change in refractive power of the lens from rest to maximum accommodation. As we can see in this image, light rays entering the eye from different distances need to be refracted to different degrees to ensure that the rays fall perfectly on the retina and form a clear, focused image. If light rays travel towards the eye from a distant source, the light rays tend to be parallel. This means that they do not have to be refracted much in order to pass through the pupil and fall onto the retina. The lens of the eye can therefore remain in its relaxed and fairly elongated state when viewing distant objects. For distant objects, the curvature of the lens must be relatively flat. When the ciliary muscles are relaxed, they hold the suspensory ligaments taut. These ligaments pull on the lens, keeping it relatively flat and allowing the image of distant objects to be focused on the retina. So the reason why the suspensory ligaments are taut, even though the muscle relaxes, as when the muscle becomes sort of floppy, relaxes, it falls backwards, it becomes smaller and causes the suspensory ligaments to tighten. However, if light rays travel from a close source, for example, reflected off a nearby object, such as your book or even the laptop screen that you're looking at now, the light rays tend to diverge. These rays need to be refracted to a greater degree so that they converge, so come back together, to be directed onto the retina. For this increased refraction of rays, it is necessary for the lens to become rounder, resulting in a focused image forming on the fovea of the retina. The increase in curvature of the lens is brought about by muscle action. So for near vision, the curvature of the lens must be increased, so it must get fatter, as a thicker lens has a greater refractive power and creates a shorter focal length. In this case, the ciliary muscles contract, so they tighten, pulling the sclera forward, causing the suspensory ligaments to slacken. As a result, the lens becomes rounder and its curvature increases, refracting the light to a greater degree and allowing a focused image to fall on the retina for the viewing of closer objects. So accommodation is the term used to describe the focusing of objects at different distances brought about by the changing of the convexity or the shape of the lens and as a result its refractive power. This change in shape of the lens results from the action of the ciliary muscles, which in turn affect the tension of the suspensory ligaments that hold the lens. An easy way to remember how it all works is that close vision requires the muscles to be contracted, so close and contract, C and C, and the result is a round lens, so the C looks slightly round. For far vision, the lens needs to be flattened, so F and F, and the muscles are relaxed. And in this case, when you write a lowercase r, it looks like a little mini version of the letter F. So the refractive power of the lens changes from low in a flatter lens when at rest to a high refractive power in a rounder lens at maximum accommodation. When a person grows older, the lens loses some of its elasticity and cannot alter its shape. There is a tendency for it to remain in its elongated shape with the muscles at rest, resulting in some people becoming long-sighted, where they struggle to see closer objects as they get older. So as you will see in this short video, the lens is able to adjust its curvature quite easily while the lens is in that elastic state where the muscles contracting and relaxing are able to cause the shape to change quite easily.
Accommodation is a healthy eye's ability to focus on objects at any distance, close up, far away, and in between.
So if we just play that again, as we can see,
Accommodation
as the
is a
flower
healthy
gets
eye's ability to
closer,
focus on objects
the
at any
lens
distance,
becomes rounder,
close up, far away,
and as it
and in
moves further
between.
away, the lens becomes flatter. So that brings us to the end of this video. So what I'd like you to do is to complete the closed passage and the labeling activity that's in your booklet under these dot points in preparation for the first-hand investigation that we will be doing in class to have a look at how accommodation works. And that to-do screen is the wrong one. So if you could just do the closed passage and the labeling activity, that would be great. Thank you.